Dear friends, welcome back. In our previous lecture, we discussed about aerofoil and the corresponding characteristics of aerofoil. We find out what is the lift curve slope, what is CD naught, CD minimum, and then CM naught or CMAC about aerodynamic CMAC, which is about aerodynamic center. And we observed it is for most of the aerofoils, it falls within 22 to 26% of the chord. And we calculated how to get CL alpha 3D given CL alpha 2D, right? We related that. Right now, let us look at what are the external forces acting on the aircraft. The whole aim of this exercise is to find out what is the weight of a system or estimate the initial estimate of the weight of the system, which is by adding up the weights of individual components, right? That's a weight breakup of the UAV. And then what is the design CL at which you want to fly, from which you can figure out what should be the corresponding area or the planform area of this UAV. Now let us look at what are the various external forces acting on this aircraft. So, as we discussed, thrust is the force that makes this aircraft to fly at the desired velocity, and we have weight acting vertically down, and due to this thrust the aircraft flies at a velocity v infinity, and because of which we have aerodynamic forces lift and drag. We have lift and drag acting along v infinity. Now, when you say v infinity like this, what does it mean? When you draw v infinity like this, it represents the direction of motion of the aircraft. So, when you say velocity, it should have both magnitude and the direction, right? So, in what direction the aircraft moves? Otherwise, what is the aircraft's path? Right. Now let us discuss a concept called flight path angle. Right. Say you have your UAV, moving at a velocity v infinity, right? So with respect to local horizontal, the angle made by this v infinity is known as gamma, flight path angle, right? Now, is there a relationship between flight path angle, angle of attack, and orientation of the aircraft, right? So to understand that, let us take up a small example. Let us consider a level road. Okay. Say I have a bike with equal front and rear tire. Say these two wheels of this bike are connected by means of this rod. Since we have equal front and rear tire, this rod will be parallel to the road here. Right. Say I am sitting on this bike. If I start moving in this direction, the free stream velocity that I face will be parallel to my path in general. So my path is parallel to the road here. So the free stream velocity is parallel to me. Say this is my v infinity. Now let us assume this is my reference line, and since it is parallel to this path, right, since I have equal front and rear tire, and the free stream is also parallel to this v infinity, parallel to this road. So the angle of attack that I face with respect to this free stream is 0. I don't see, assuming this rod is my reference line, I don't face any angle of attack, and moreover the path that I am following is parallel, right? So the angle made by this V infinity with respect to this plane road is 0. Right? Gamma is 0 here, since it's a horizontal road. Right? So I don't have any flight path angle or the and as well as since my path is parallel to the ground. At the same time, I don't see any angle of attack in this case. Now say suddenly I encountered a flyover which is inclined to local horizontal or the initial horizontal road by an angle gamma, right? So with the same bike, I start moving on this flyover. Right? So the free stream now will be, since I am moving in this direction, the free stream will be opposite to me. Right? Again, I am moving parallel to this flyover, the free stream will be parallel to this flyover. Say this is my V infinity. Right? Since I have level tires, equal diameter tires, I still face 0 angle of attack here. Alpha is 0. What I have, but my free stream velocity is inclined at an angle gamma, which is nothing but the path in which I am moving. Right? So the path in which I will be moving is gamma here with respect to horizontal. Now say on the same road, I have changed my bike. Say I have a bigger front wheel and a smaller rear wheel. So let us say we connect this front and back tire by means of a rod. Say I am sitting on this. I start moving in this direction. Right? So I will start facing stream opposite to me and which is parallel to this ground since I am moving parallel to this. So, but in this case what I see is an angle of attack alpha because this free stream V infinity is making an angle with my reference line alpha here. So in this case I have an alpha, right? And since I am traveling on the same road, right, I will face a flyover after a while. Say this is gamma again. Now I am traveling with a different bike compared to this case, right, with a bigger front wheel and a smaller rear wheel. Now again the free stream will be parallel to my path and my path is along this flyover which is inclined at an angle gamma. That means my free stream V infinity gives the direction of my path. If I know what is the angle measured with respect to this free stream, that means that angle is equals to the angle at which my vehicle is actually moving, right? So in this case, since I have a bigger front wheel and smaller rear wheel, in this case I will see certain angle of attack, right? As well as I am moving on an inclined path which is gamma. So what is my total orientation now? Let theta represent the total orientation with respect to, which is measured with respect to horizontal, right? So in this case, what is my orientation? 0. In this case, gamma with respect to horizontal. So in this case, my orientation is alpha, right? Here it is, my orientation is alpha plus gamma. Right? So similar to this case, say when you are traveling on a level road, right, you still have an orientation, which doesn't mean that since you are sitting in this at this angle, it doesn't mean that you are moving in this direction, right? That means you can still have an angle of attack when you are traveling horizontal or parallel to the ground, right? Even when you are flying at a level flight condition, you still have an angle of attack. So in which the gamma is 0 in this case, right? Because gamma is measured with respect to local horizontal, right? So now let us come back to this aircraft. So this is my FRL, fuselage reference line. So my angle of attack is defined with respect to this fuselage reference line. Say this is my V infinity. So what does it mean? So my aircraft is actually moving in this direction, right? Along. That's why you face V infinity opposite to you. So the free stream will be opposite to the direction of your motion, right? So this angle, say, is the angle of attack, right? Say this is my local horizontal, or say this is my ground. Right? So the angle made by this V infinity with respect to this local horizontal is gamma. Right? So if I can represent that local horizontal here, okay, these two are parallel. So this angle is gamma, right? And this is alpha. Now the orientation of the aircraft is theta, which is alpha plus gamma. So gamma gives the direction of your motion. Let us consider an aircraft moving in a vertical plane, right? Moving in this vertical plane, constrain our motion of this UAV to this vertical plane. So let W act perpendicular to the local horizontal, right? Is a weight acting perpendicular to local horizontal. Let T be the thrust vector, which is along the fuselage reference line, FRL. And say the aircraft is moving with a velocity V infinity, right? And this angle is known as angle of attack. So with respect to local horizontal, so the aircraft is moving with V infinity in the direction gamma, right here. Yeah. Now what will be the direction of drag along V infinity? This is drag, and you have lift, which is perpendicular to V infinity. So this is lift. Now let us now write down equations of motion along the flight path and perpendicular to flight path, right? So that is along V infinity and perpendicular to V infinity. So the component of W, which is acting along perpendicular to V infinity but in negative direction of lift, is W cos gamma, and the component of weight acting along D is W sin gamma, right, where this angle is gamma. We know V infinity and this negative lift line are perpendicular. So we know this angle is 90 degrees, 90, this is 90. So you know you have this as gamma, right? This is your local horizontal and weight acts perpendicular to local horizontal. So this angle is 90 degrees again. Okay. But this angle is gamma. The V infinity makes an angle gamma with respect to local horizontal. So what about this angle? 90 minus gamma. This becomes like 90 minus gamma. So this particular portion is 90 minus gamma, and this is 90 degrees. So 90 minus gamma will give you gamma. This is your so this is gamma, right? So a component of W acting along negative lift is W cos gamma, and along the drag is W sin gamma. And say this is your thrust misalignment. So it is not necessary that thrust is along fuselage reference line. Okay. So let us make it a bit complicated. So thrust is not along FRL, right? Say this is your thrust line, and this is your reference line. So let me take another chalk. This is your fuselage reference line, right? This is your FRL. Right? So this thrust is misaligned. So now the angle of attack will be with respect to fuselage reference line. So this is your V infinity. So this angle is alpha. Right? Now this T is misaligned with V infinity by an angle epsilon. So your T is not acting along the direction of your motion, right? So now the component of T along your direction of your motion is T cos epsilon, and perpendicular to the direction of motion, which is along the direction of lift, is T sin epsilon. Now let us write equations of motion for this case. Say this particular aircraft is rotating in this vertical plane about a center point O, which is of radius R1. Right? This is performing a loop at the same time. Now, according to Newton's second law, the total external forces acting is equals to rate of change of linear momentum, assuming mass is constant, d by dt of v bar. Right? So what are the external forces here? Thrust, lift, drag, and weight that are acting on this aircraft. So now let us consider a unit vector along lift direction is eta, and a unit vector which is parallel to flight path angle is zeta cap, right? So this is your positive direction of your eta cap and along the lift, and this is the positive direction of your zeta cap. So the total external force is force which is parallel to gamma into zeta cap plus sigma f. You should say it's a total external force, right? So sigma f, which is perpendicular to gamma, that is perpendicular to gamma is perpendicular to free stream velocity here along eta direction, right, is equals to m into dv bar by dt. Let us rewrite those equations here. So the total external forces, F external, is equals to rate of change of linear momentum, right? So while handling these equations, we assume that the aircraft is a point mass acted upon these four external forces, right? So this is sigma f external, which are parallel to gamma, and the corresponding unit vector along gamma is zeta cap plus total external forces which are acting perpendicular to gamma eta cap is equals to mass into acceleration which is parallel to gamma into zeta cap plus acceleration which is perpendicular to gamma into eta cap, right? Now let us consider the forces or the equation of motion along the flight path angle, which is by comparing the coefficients of zeta cap, right? So total sigma f external parallel to gamma is equals to, what are the forces? Positive forces here is like, what are the total forces acting along zeta cap? T cos epsilon, d and W sin gamma. So T cos epsilon is in the positive direction, D and W sin gamma are acting along the negative eta cap direction, zeta cap direction, sorry. So the total external forces are T minus D, T cos epsilon minus D minus W sin gamma is equals to mass into acceleration, which is parallel to gamma. Since v infinity is the velocity along this direction, the acceleration will be, and it is assumed, I mean the aircraft here is assumed as a point mass. So acceleration we can represent it as d infinity by dt. So say this is your first equation. Equation number 1. Now consider the second equation. Zeta f external, which is perpendicular to gamma, is equals to, what are the forces acting perpendicular to flight path angle? Or lift and T sin epsilon, or along the positive direction of eta cap, right, along the positive direction of this axis, and W cos gamma along the negative direction of this. So what you have as an external forces perpendicular to flight path are L plus T sin epsilon, lift and a component of thrust due to its misalignment, minus W cos gamma is equals to mass into acceleration perpendicular to gamma, right, flight path. Now we assumed that this aircraft is rotating about this about O, right, which means O is the center of this rotation, which is at a radius r1. So what will be the perpendicular acceleration here? V square by r. Right. So what do we do with these two equations? What is the motive? Consider a typical profile of a UAV. Say this is your home, right? It initially has to take off. This is taxi and take off, and then climb, and then cruise, right? And then take a turn and cruise back to home, descent and landing at required position or the launch position. Or there can be another mission where you want to send unmanned system from one location to the other location, which also involves a takeoff, cruise and landing. Say this is your point B, this is your point A. So if you want to send this UAV to another location, which also involves a takeoff, climb, cruise, descent and landing. Takeoff and taxi, climb, cruise, descent and land. Right. So these are the typical mission for any UAV, or in fact, if you want to generalize, for any aircraft. Right. Now, what should I do if I want to perform this mission? Say I have an aircraft. First of all, I need to know what should be either the fuel or the battery that I need to carry so that I can perform this particular mission. When you say either fuel or battery, it means you need to carry so much energy, right? So first you need to know what is the requirement of this particular mission, or the requirement of the system to perform this particular mission, right? And also, in order to perform this mission, you need to produce thrust, right? And it's a variable thrust because it has to undergo various phases. So the thrust has to vary. And moreover, we will be talking more in terms of a propeller driven aircraft, right? So we need to produce enough power, right, to perform this particular mission. So first of all, we need to install an engine which is capable of producing the required power by the system, right? How do you know that? How do you get to know? Or in other words, which engine you want to install for this particular aircraft to perform this particular mission? And what should be your fuel weight or overall weight breakup? How do you get to know for a given mission requirements, if I want to build a UAV, what should be the weight breakup, or what should be the overall takeoff weight? How do you estimate it? And finally, how do you design the wing of this UAV? Right? So the answer comes from these equations. So these two equations are going to help us to address all these questions. Before proceeding further, so for any design to start with, or say if you consider a bike, right? So you see there are many specifications, right? It accelerates within so much time, and it has got an engine with so much power, right? If the maximum speed is this much, and the minimum speed, like, or the most economic speed is 40 to 60 or something. So all these are ratings of the system, right? Do you think whether these ratings have come after the design as a result of the product, or they were considered before design? If you ask me, I'll say, yes, I want these requirements from this system, or I want these specifications to be the output of this system, and I have designed my system and I selected the engine accordingly. So that means you have to specify your requirement beforehand, before initiating the design. So what you call it as mission requirement. So mission requirements are taken as an input to the design process, right? Say initially, you take these mission requirements and you use historical database to perform configuration selection. So what does this configuration selection includes? You need to design what should be the wing planform. Are you going for a wing alone configuration? Do you have a fuselage, or have you blended the fuselage into the wing? Or do you need a tail? Right? If you need, why? And what should be the size of the tail? And how far the wing and tail should be placed? Why there is a T-tail? Why there is a conventional tail? So all these questions to be addressed, right? So that is the configuration selection here. So in this course we'll look at the glimpses of all these things, right? Whatever we are going to discuss in this flowchart. So once you select the configuration, so that means the output here is a three-dimensional 3D model, right? 3D model, where you have the aerofoil selection and the wing planform geometry and the tail sizing and the control surface sizing. So you can get it as an output from this configuration selection. And see whether this configuration selection satisfies the mission requirements or not. It's like performance analysis. Right. You also work with simulation. Say certain parameters, if you want to have the system certain parameters, so that you can have a better control over the system and better performance, right, in terms of aerodynamic parameters, which are generally observed by simulation. So this, in order to achieve that, those parameters, what should be the configuration? It's not that just from the configuration you do the simulation. It's that whatever the parameters that satisfies the simulation, right, and which are in general address most of the problems like control and all, right. So if you want such parameters to be reflected in the system, so what should be the configuration? Similarly, you have assumed some performance mission requirements, right, in which you might have specified some performance parameters. So this again a vice versa. If you want this performance parameter, what should be the wing size or the wing loading or the thrust loading? Or say if you want such a rate of climb, what should be the engine that you need to install on this for this particular UAV? What should be the specific fuel consumption? So all this comes here. So mission requirements will drive the entire design process, right? And then again, they are interlinked. Simulation and performance, again, they are interlinked. Coming back to this typical mission profile, we witness there are various phases during a particular mission that a UAV has to perform. So here, let us say this is your home from which you are launching your UAV. It has to accelerate to the desired velocity, and then, so during this acceleration phase, we can term it as takeoff and taxi, right? So, and then it will climb to the desired altitude, and it performs the mission that you require. So this mission is mostly a cruise or a steady and level flight, right? And then it will come back to the approach point and then start approaching the home by descending to the ground, by descending to the required and then it will take an approach, descent and landing. So if you look at this entire profile, so the maximum time this UAV will spend performing cruise, right? Now you have to design your system, whereas the climb hardly takes around 2 minutes because it's an unmanned, it can have higher rate of climbs, right? And descent will hardly a gliding flight in most of the cases, and then landing, yeah, of course, maybe for a couple of minutes. So the major part is during cruise. The major part this UAV has to perform is cruise, right? Where it involves maybe 2 hours of flight, 3 hours of flight, or 40 minutes of flight. So the ratio of times, like the ratio of time that it spent for cruise and to the other phases of flight is very high. Or in other way, the ratio of other phases of flight and the cruise time is very, very less, right? So now whatever the design that you have to perform is for this cruise flight. So now let us look at what should be the power requirement or the wing required, right, to say what should be the wing required to lift the UAV of weight W, right? So we have to design this wing for this cruise. Now let us look at cruise flight. So what is this cruise flight? It is steady plus level flight. So what do you mean by steady? the constant velocity flight, right, and level flight. So earlier we discussed, right, what is level flight. Consider this is your ground, say this is your UAV flying at a geometric altitude of hg at time t1. Now over a delta t, say t2, you again measure the altitude of this UAV, say it is hg2 and it is hg1. So over this delta t, this hg2 minus hg1 remains same, right? If it remains same, then you say it's a level flight. So if you have level flight, that means the flight path will be parallel to the local horizontal. So gamma is 0. That means gamma is equals to 0, right? And further assume there is no thrust misalignment, which is epsilon 0. So the total assumptions here are it's a steady flight and level flight without any thrust misalignment. Now let us look at how these equations of motion in this vertical plane reduces to. So substituting those epsilon naught and steady condition and level flight condition in equation 1 and 2, we have, since it's a steady flight, the acceleration is 0, both parallel and perpendicular components of acceleration are 0 there. So there is no misalignment further. So cos epsilon, cos 0, t cos 0 minus d minus w sine of gamma is 0 again here is equals to 0. This implies t minus d is equals to 0, that is t is equals to d. So this is my equation C1, which is equation for cruise 1, all right. And now substitute the same conditions for equation 2. What you have is L plus t sine 0 minus w cos 0 is equals to mass into acceleration, perpendicular acceleration to flight path angle, which in this case is 0, right. So this is L minus W is equals to 0, which implies lift is equals to weight of the system. If these two conditions are satisfied, you can have a level flight, right, which is a steady and level flight. Now say if you have a mini jet engine, if you want to install on it, right. Now thrust is equals to drag and lift is equals to weight, right. Now what are the velocities that you at which you can achieve this cruise flight? Or in other words, what should be the range of velocities that are possible to have a cruise flight, right? So you have t is equals to d from C1, and from C2 you have L is equals to W. See, what is t is equals to d? So in this case, how does the aircraft look like? Say this is your FRL, fuselage reference line, and this is your V infinity. That means the aircraft is moving in this direction, and this is your alpha, and weight is acting perpendicular to the free stream, to the local horizontal, and lift is acting perpendicular to free stream, and you have thrust along the free stream. Since there is epsilon is 0, you have thrust along free stream and drag acting along the free stream. So this V infinity is parallel to local horizontal here. That means gamma is 0. Right? So in this case, if you want to have a level flight, whatever the drag that is generated by the system should be overcome by the thrust. That means drag is the requirement of the system to move at that particular velocity, right? For example, so T is equals to D into half rho V square S into CD. Okay, drag is not the requirement. In fact, drag is the system's output, right? Is a response of, it's an output from the system when moving at that particular velocity. Now, this is a negative force, right? Now the system has to generate thrust, which is equivalent to this drag in order to have this level flight. That means this is required by the system to perform this particular level flight at this velocity V infinity, right? So what I can do is thrust required is equals to W by L by D, right? So dividing equation 1 and 2 by performing a simple manipulation like T by W is equals to L by D. This implies thrust required by the system is equals to W by L by D, D by L, sorry, D by L, which is L by D, that is equals to W by CL by C. Here, which is W by CL by C. Now, what should be the minimum thrust that the aircraft has to produce so that you can still have a level flight, right? So this minimum thrust required minimum is equals to the maximum L by D, right? So if you have this L by D maximum, you can get the corresponding minimum thrust required for this particular UAV of weight W. So what is CL by CD maximum? How can you get? Differentiate with respect to CL and equate it to 0. Why CL? Why not CD? CD is a function of CL, right? CL is the variable here. So where CD is equals to CD naught plus K into CL square, right? So this implies CD square into CL, okay, into CD naught plus KCL square minus CL into 2KCL is equals to 0. How we got this? du by dv is equals to u dash v minus uv dash divided by v square, multiplying by CD square on either side of this equation. What you have is KCL square is equals to CD naught. Yeah, this is 2KCL square and this is KCL square. You have to take it to the right hand side. You will get KCL square is equal to CD naught. This implies CL is equals to root over CD naught by K, where you know K is since and K is equals to 1 by pi E AR. You know how to calculate aspect ratio, and you need to know what is the Ostwald's efficiency of this UAV, right? Then you will be able to find out what is the corresponding CL condition for L by D maximum. L by D max or CL by CD maximum condition. This is a CL condition. Now what will be the CD for L by D max? CD is equals to CD naught plus K into CL square. CL for L by D max, max square. This is equal to CD naught plus what is CL for L by D max? It is CD naught by K. So this say equation 1 for this case. from equation 1, or say C3, crew is equation 3. So this is C3, K into CD naught by K, which is equals to CD naught plus CD naught. Okay, so this particular term is known as induced drag coefficient. Induced drag coefficient. This is profile drag coefficient. Right. So in this case, during L by D max condition, your profile drag is equals to induced drag, right? So the total drag coefficient here is for L by D max, which is equivalent to 2 CD naught, right? Now what is L by D max? Is equals to CL for L by D max and CD for L by D max. This equals to square root over CD naught by K divided by CD naught, 2 CD naught. This is equals to 1 by root over 4K CD naught. You see here, it is L by D max is 1 by root over 4K CD naught. Now how do you get minimum thrust requirement of this system? We need to substitute this L by D max, CL by CD max condition here. So this equals to W into square root over 4K CD naught. So thrust required minimum is obtained by L by D maximum. Which is W into root over 4K CD naught. So you can calculate what is the minimum thrust requirement to achieve this level flight if you know the information about the weight of this UAV and the induced drag correction factor and CD naught, profile drag coefficient, right? If you know this information, you will be able to figure out what is the minimum thrust required. Now say, if you want to fly at this minimum thrust required, how do you do it? Or say, will the pilot understand fly at this W into root over 4K CD naught? No, we need to translate to his language, right? So what he can understand is what should be the velocity of flight, right? Now we will figure out what should be the corresponding velocity of flight to achieve this level flight with minimum thrust requirement. So we have C2. From C2 we have L is equals to W. Right? So this equals to V infinity, which is half rho V infinity square is equals to W. SCL is half rho V infinity square, SCL is equals to W, and V infinity is equals to root over twice the wing loading divided by rho into CL. Now velocity for thrust required minimum, V for TR minimum is equals to root over twice the wing loading and the over density of the air at that particular altitude, right, into CL for TR minimum. What is the value of CL for the corresponding thrust required minimum? This equals to square root over 2 times W by S divided by rho into what is CL for TR minimum? CL condition for L by D maximum. So when is this thrust required is minimum? When you have L by D maximum. How do you achieve this L by D maximum? When CL is the corresponding CL and CD for L by D max. So the corresponding CL for L by D max is root over CD naught by K. Right. So this implies velocity for thrust required minimum is equals to root over 2W by S divided by density into root over CD naught by K, that is K by CD naught raised to the power of 1 by 4. This is the corresponding velocity at which you need to fly if you want to maintain minimum thrust requirement, right? And you still have a level flight. Right. Say if you don't want to fly at this minimum velocity, right, or minimum thrust required velocity, since your mission may demand you to fly at a different velocity, right? So what should be the solution? What will be the corresponding thrust required there? Right? We'll discuss that right now. Now let's have a closer look at this equation. C1, thrust required is equals to drag, which is half rho v square S CD. And from C2 we have L is equals to W, which implies half rho v square S CL is equals to W, where CL is equals to 2W by S by rho into V infinity square. Now thrust required is equals to half rho V infinity square S into CD naught. We express CD as the in the form of drag polar, CD naught plus KCL square. So you can get CL from here, substitute this CL in this equation. So thrust required is equals to half rho V infinity square S CD naught plus half rho V infinity square S K into CL square, which is 4W by S square divided by rho square or rho infinity square V infinity power 4, right? This equals to TR equals to half rho V infinity square S into CD naught plus 2 kW square 2 times kW square by S by rho so V infinity to the raised to the power of 4 into half rho S CD naught CD naught minus TR into V infinity square plus 2 kW square divided by rho S is equals to 0. So what are the roots of this equation? So V infinity square is equals to minus B plus or minus root over B square minus 4AC 4 into half rho S CD naught into 2 kW square divided by rho S divided by 2A rho S CD naught SS cancels out, rho cancels out. So am I correct? TR by W is a thrust loading into wing loading plus or minus wing loading to square root over TR by W whole square minus 4K CD naught divided by rho n. Right. Now let us look at how this thrust varies with velocity. Thrust and V infinity. It's a typical variation of thrust with velocity, thrust required with velocity, right? So this is the point of minimum thrust requirement, that is TR minimum, and the corresponding velocity for TR minimum, which is obtained by L by D max condition. So the CL for L by D max is root over CD naught by K. So you have to trim your aircraft to achieve that CL in order to fly at this particular V infinity, right? So that you are flying at a minimum thrust requirement condition, right? And the corresponding angle of attack for trim we can find out by using the linear expression of CL, where CL is equal to CL naught plus CL alpha into alpha, right? Now this is your minimum thrust required condition. Now see, if you observe here, for a given thrust requirement, you can fly at two different velocities, V1 and V2. Say if you want to fly at this particular thrust required condition, TR. So the options that you have is either you can fly at V1 and V2. So which velocity you need to choose? Okay. Let us divide this plot into two halves based upon the minimum thrust required condition. So by the way, when this minimum thrust required occurs, that means you have a unique solution here, where if this discriminant is equals to 0, you will get this unique solution, right? You will get a single velocity. So what is the discriminant? TR by W whole square minus 4K CD naught is equals to 0. This implies TR by W is equals to root over 4K CD naught. This equals to TR is equals to W into root over 4K CD naught. So is it not the minimum thrust required condition? This is the minimum thrust required, TR minimum. Minimum thrust required condition, right? Where L by D max is 1 by root over 4K CD naught. What is thrust required is W by L by D, right? So this particular point corresponds to that particular, this point corresponds to this thrust required minimum condition, and the corresponding velocity you can attain. So if you equate it to 0, then you will have a unique solution, right, from which you can find out what is the corresponding velocity of flight. Now say if I want to fly at this thrust required condition, right, if I fly, then what is the velocity that I have to choose? V1, there are two solutions here, right? You have plus or minus here, you have two solutions. Now which velocity you need to choose to fly? Now let us define So what is equilibrium? The state of the system about which resultant forces and moments acting are zero, right? That means there is no acceleration, either linear or angular, right? Either the body is moving at a constant velocity. Now we can say cruise is a steady and level flight where there is a constant velocity, right, which is equals to equilibrium. So if you are flying at different velocities, that means you are producing different thrust required from the engine. Ultimately you have to supply that thrust required to the system, right, to the UAV. So that thrust required need to be generated from the engine, right. Now when you are flying at different thrust required condition and different velocities, all these points are equilibrium points as far as level flight is concerned, right. So aircraft have a range of equilibrium conditions, right. Now what is equilibrium here? Resultant forces and moments are zero, okay. Now let us consider velocity v2, right. Now due to some external, during this condition, if you are flying at velocity v2, or during this discussion, let us assume the pilot from the ground station has set the throttle of this UAV to a particular setting, right, has trimmed the UAV to a particular throttle setting. Now we are not controlling the UAV, right. Now say there is a sudden gust which has increased the velocity. Now say this is the direction of increased velocity. Now say this increase in velocity will take you to this point. Let us say let this be v2 prime. Let this be v2 prime. So this is the point that has increased the velocity. So the corresponding thrust required is Tr prime or Tr2 prime at this case. So that means the thrust required has decreased, but the throttle is the engine is delivering higher thrust and you are not touching the throttle, right. Now the thrust required decreased and the drag is decreased eventually. That means the drag is reduced. So the vehicle accelerates. There is a excess force that accelerates the system. This is the difference of. So the vehicle try to further accelerate, that means the velocity further increases, and the say this to be v2 double prime, and the corresponding thrust requirement decreases, v2 double prime, this is your Tr2 double prime, this has decreased further. So your drag decreases, the drag of the system decreases, and this further accelerates. So you are not coming back to your initial equilibrium, right. Now say we assume that there is a increase in velocity because of the disturbance. Now say there is a decrease in velocity because of the disturbance. So again we have come back to our original equilibrium. Say this is my v2 comma tr, v2 comma tr is the corresponding coordinates of this, right, of this point. Now say the velocity has reduced because of some external wind disturbances, right. Since we are not touching the throttle here again, so this reduced velocity will result in a increased thrust here. The corresponding thrust requirement of this point is Tr, let this point be Va2, right, and the corresponding thrust requirement is Tra2, right. So this has, at this particular velocity, the thrust requirement has increased, which means the drag of the system has increased, right. Now this increase in drag will decelerate the system. That means the velocity further decreases. Say it will come Va2 prime, say this is your Va2 prime, and the corresponding thrust is Tra2 prime. So this is your Tra2 prime, So that means the thrust requirement has increased further, right, which will decelerate the system further. That means the UAV is not coming back to its equilibrium by itself. Either the pilot has to give a constant increase and decrease in the throttle, even for a small disturbance. Now let us look at the other solution here. Let this point be the other solution. Why? Because this, if you want to fly at this TR, either you can choose this velocity V, V2, or you can choose V1, right? Thrust. Say this is the point of my interest, thrust required at this particular location. So I can achieve this level flight either by flying V2 or V1. So from this equation, right? Either V2 or V1. Now we understood if I fly at V2, I need to give a constant correction to this, right? It can't come back to its equilibrium by itself. Now say if I am flying at V1, say if, again let us repeat the same story, like you have a disturbance that has increased the velocity of the system. That means this is your increased velocity. So V1 prime, right? So this V1 prime will also increase the thrust required by the system, right? Let this be TR1 prime, right? So this has increased since the thrust requirement increased, and moreover you are not touching the throttle of the system. You are not giving the extra energy to sustain this velocity, right? So the vehicle decelerates. That means the velocity decreases. That means you start coming towards this point, from this point to this point, right? And now say if your vehicle velocity is decreased because of external disturbance from V1 to V1 double prime, okay? Now the corresponding thrust requirement is also reduced. So from this plot you can see the corresponding thrust requirement also reduced. So compared to TR1 double prime is lesser, right? So since you are not touching the throttle again, this additional thrust that is available will accelerate the system to the trim velocity or the earlier equilibrium velocity. That means without any external control, if there is any disturbance, if you are flying at this point, the aircraft will automatically come back towards its equilibrium. That's why to the right side of this line, it is known as stable region of flight. That is velocity for stable region of flight. This is the unstable region of flight, right? So stability is an inherent property to come back towards its equilibrium once disturbed from it, right? It should come automatically. Now why it is coming? Why this curve looks like this? We'll discuss in the coming lectures.